So hello, everybody. So this is joint work with Andrea Montanari at Stanford. So in this talk, I'm going to talk about computational and information-theoretic thresholds for statistical inference. In particular, in the paper, we treat the case of generalized linear models. But for this talk, I will restrict myself to the case of phase retrieval for the simplicity of explanation. So let me first present the model. So in phase retrieval, the problem is the following. So we have a signal X, which is our target to recover. And this signal is d-dimensional, and we can think about it as having elements in the complex field. Then what we observe is some function of the scalar product. So we have a sensing matrix, which is obtained by sensing vectors AI, and we have n sensing vectors AI. And we form the scalar products between X and the sensing vectors. And for the special case of phase retrieval, what we observe is the modulus squared of this scalar product here plus noise. For example, you can think about the noise as being Gaussian, but the distribution doesn't really matter that much. And this is a relatively famous and well-studied problem in signal processing because of its application in X-ray crystallography, microscopy, interferometry, and so on and so forth. Now, again, everything that I will say, it's kind of valid also for generalized linear model, in which here you have just some conditional distribution that you can choose. So now there are two main ways to solve phase retrieval. The first one is just to relax it to an SDP and then solve the SDP. And here is a bunch of papers that do that. Now, the main problem of this approach is that typically if these the order of a few hundred or 1,000, this becomes computationally prohibited real quick. So people have tried also to solve directly the non-convex least square problem. And for example, some algorithms to do that are alternating minimization, approximate message passing, or Wirtinger floor, which is just a fancy name to say gradient descent. Okay. Now, the thing that I want to say is that all these approaches share the same general strategy. So the idea here is that you're going to initialize your algorithm somehow, and you're going to obtain some estimate x hat, and then you're going to improve your estimate iteratively via some iterative method. For example, in Wirtinger floor, this is essentially gradient descent. Okay. So this basically motivates the problem, the weak recovery problem, in which essentially what we want to study is how hard it is to derive this initial estimate. Okay, because typically this is the real bottleneck of our computation. So the weak recovery problem can be formalized as follows. So there is some signal x that we want to recover. X has dimension d, and we are given n measurements yi of the signal x, which in the case of phase retrieval is essentially scalar product of x with a Gaussian, modulus squared plus noise. Okay? And our goal is to find an estimator x hat such that this estimator is positively correlated with x. So you can think about the norm of x and x hat to be 1. So what we want is that the correlation between these two vectors is larger than, say, 0.01, something like this. Now, this problem is parameterized by the ratio delta between the number of measurements and the signal dimension. Now, obviously, if delta is larger, the problem is easier because I have more stuff. I have more measurements. And if delta is smaller, the problem is harder. So what I want to unveil here is that there is a phase transition in the sense that the problem is impossible up to some point, information-theoretically, and then when it becomes information-theoretically possible, it's also algorithmically solvable. So that's the main result that I would like to present. So let me first state our main result in somehow an informal fashion, and then I'm going to be a little bit more specific later. So let x be a complex vector in d dimensions, and I want to recover it from n measurements, yi. And it's important that the measurement matrix A is Gaussian, and let delta be equal to n over d. Okay? Now, if delta is smaller than 1, so if n over d is smaller than 1, then the problem is information-theoretically impossible. So this means that no algorithm can provide any non-trivial estimate on x. Okay? So in this regime here, we cannot solve the problem. On the other hand, if delta is larger than 1, then the problem is easy. And by easy, I mean that there is a simple spectral algorithm that can solve it. So let's say with complexity n cube, we can solve this problem. Okay, very good. And as I mentioned at the beginning, we can extend all this thing, and we can compute thresholds also for generalized linear models. So we have a phase transition here. So in the remaining part of the talk, I would just like to state a little bit more precisely what is the information-theoretic lower bound and what is the spectral upper bound. And for details about the proof of these two things, just come to my poster later this evening. So as concerned the information-theoretic lower bound, let me mention also a related work by Leo here in the first row that he presented yesterday. And what he showed yesterday is that the prediction for the mutual information given by statistical physics via the replica method is actually exact. So that provides a computation for the mutual information and also for optimal errors and a bunch of other things. So that's a certainly interesting related work. So what we do here is the following. So let me define the matrix MMSC. So the matrix MMSC is 1 over d squared because this is a d by d matrix, so this term here is just for normalization of the expected value of the Frobenius norm. So this is the sum of the squares of this matrix here. So this is the thing that I want to estimate, x transpose, minus the Bayes optimal estimator. So this thing is the expected value of my target given everything. So given the measurement matrix, which I know, and given the measurements. Okay, so this is the optimal estimator, and in general, it's exponentially hard to compute it. Now, if the MMSC is equal to 1, then this means that the optimal estimator gives you 0. So this is bad. So this essentially means that the best thing that you can possibly do is just plug in 0 and call it a day. Okay. So what we show is the following thing. So suppose that delta is smaller than 1, and this is the setting in which we work. So we let x be uniform on the sphere. We read the vectors ai to be Gaussian, as I mentioned at the beginning, and yi be obtained according to the phase retrieval model. So we have modulus squared plus Gaussian noise. Then, in the limits of vanishing noise, the MMSC tends to 1 as n goes large. So in the high-dimensional limit, essentially, no estimator can do anything for delta smaller than 1. And the idea to do this is essentially a computation of the conditional entropy via a second moment method. And okay, I will not talk about this more here. I can talk about this maybe later in the poster tonight. Okay, let me talk about the spectral upper bound. So this is a relatively standard thing to do in this kind of problem. So what we do is that we form a matrix by taking some modulation on the data. So we take the data yi, we apply some preprocessing function tau, and then we multiply by ai star. Okay. So if tau is, for example, the identity, this was done a few years ago, and this was the spectral initialization for alternating minimization in the original algorithm of 13. So one question, for example, is what is the best preprocessing function? So in this paper, we also answered this question. So the spectral estimator is the principal eigenvector of this matrix here. Okay. So essentially what we show is the following. So let x, ai, and yi be defined as before. So x uniform over the sphere, but for this case it doesn't really matter because everything is rotational invariant. So you can pick any x which has an assigned norm. But it's really important that the vectors ai are Gaussian. Okay, then for any delta larger than 1, pick this preprocessing function here, which we will show to be the optimal preprocessing function. Then we have positive correlation between the estimate x hat and the real vector x. Okay, so this means that we can achieve weak recovery. And the idea for this is to characterize exactly the spectrum of the n. Now, if you know a little bit about this, the typical way in which these problems are solved are via matrix concentration inequalities. Okay. So typically what people do is that they compute the expected value of the n, and they show that in this case, this gives a good estimate, and then they show that the matrix doesn't vary too much with respect to the expected value. But these bounds are not tight. So in order to get tight bounds, what we get is that we compute exactly the spectrum of the n. And what we want to unveil is that there is a phase transition. So when delta is smaller than 1, the empirical spectral distribution of the matrix looks like this. So it's a bulk with all the eigenvalues here. And the principal eigenvector is uniformly random. But when delta is larger than 1, the principal eigenvector escapes from the principal eigenvalue escapes from the bulk, and the eigenvector becomes correlated. So that's essentially the geometric picture for this problem. Okay. Now, okay, I'm running out of time, but the only thing that I want to mention is that this algorithm works really well in practice too. In particular, in this case, the sensing matrix is not Gaussian, but it's a variant of a Fourier matrix. This is called coded diffraction patterns. And so we show that, for example, we do much better than by doing a relatively popular algorithm, which is truncated initialization by Chen and Candesso a couple of years back. And I mean, you can observe visually that we obtain much better results. Okay. So again, in general, this holds for generalized linear models. So we have a lower threshold, information theoretically, an upper threshold, spectral. And we also show that the upper threshold, which is spectral, is the natural threshold for the AMP algorithm. And I can detail this in the poster tonight. So thank you very much for your attention.
Time for one question while the next speaker gets ready.
Yeah.
Yes.
Do you have any results from an AI
No. No, it's difficult. I mean, one other case that might be tackled is the case of hard distributed. So you take the matrix A sensing, orthogonal, and take a uniformly at random among the group of orthogonal matrices. Because the fact is that, especially the upper bound is a random matrix theory result. So if you don't know the spectra of random matrices of that class, then this is going to be very hard, I think. One case that would be interesting is the Fourier case.
How about you just uniform over 0?
Uniformly at random, I think you could do. But Fourier case, I think, is the most interesting because that's what people do.
All right, so let's leave the rest of the questions to the poster and thank Marco again.
Thanks.